Albert Einstein called it spooky action at a distance. And honestly, he wasn't wrong. Imagine two objects on opposite sides of the universe that can communicate instantly, faster than the speed of light. Hi, I'm your narrator name, and today we are going to demystify quantum entanglement. We'll look at what it actually is, how it works with a simple coin analogy, and how quantum computers use it to do things classical computers can only dream of. Let's dive in. So, what is entanglement? In the classical world, our everyday life, objects are independent. If I have a red ball and you have a blue ball, what I do to my ball doesn't change yours. But in the quantum world, particles can become entangled. This means they link up and become a single system. Even if you separate them by billions of miles, you cannot describe one without the other. They lose their individuality and become two halves of a whole. This can get heavy, so let's use an analogy. Imagine you and I each have a coin. In a normal world, if I go to the North Pole and you go to the South Pole, and we both flip our coins, the results are totally random. I might get heads, and you might get tails. My result has nothing to do with yours. But imagine these are quantum entangled coins. We separate them by thousands of miles. While they are spinning, they are in a superposition, undecided. But the moment I catch my coin and look at it, if I see heads, your coin will instantaneously force itself to be heads too. If I looked and saw tails, yours would instantly be tails. There is no text message, no signal, no Wi-Fi sent between them. It happens instantly. The measurement of one determines the reality of the other. That is entanglement. Now, let's apply this to an actual quantum computer. We don't use coins, we use qubits. When we entangle two qubits, we put them into what is called a Bell state. Mathematically, it looks like this equation on the screen. But don't let the math scare you. All this equation says is that the qubits are in a state of 2,000 foot and 11 at the same time. This means that when the computer measures them, there are only two possibilities. Option A, both qubits turn out to be 0. Option B, both qubits turn out to be 1. It is impossible to find one qubit as a 0 and the other as a 1. They are perfectly synchronized. Why is this useful for computing? Well, this link allows us to do things standard computers can't. One example is superdense coding. Because the two qubits are linked, we can manipulate just one of them to send 2 bits of classical information. It's like getting a buy one, get one free deal on data transfer. It also enables quantum teleportation, moving the state of a particle from one location to another without physically moving the particle itself. Entanglement proves that the universe is far more connected than we ever thought. If you want to learn more about how quantum computers actually process this data, check out our next video on quantum gates. Thanks for watching. Don't forget to like and subscribe for more complex science, explained simply. See you next time.